we cannot use FTC. We cannot use the fundamental theorem of calculus, FTC. Okay, so because the integrand 1 over x is undefined at least one number on the interval, the function 1 over x is undefined at 0. So the integral is a type 2 improper integral. Okay. Now let's recall the difference between type 2 and type 1. Type 1 is when one of the lower limit and upper limit is infinity. In that case, you have a type 1 improper integral. Now, if the function is undefined at some point on the interval from 0 to 1, then you have a type 2 improper integral. Okay. In this case, the function is undefined at 0. Okay. So 0 is the point with the problem. 0 is the reason why we have a type 2 improper integral. Right. For this one, I don't think I have to mention the geometric meaning. We have seen it before, right? So geometrically, we are trying to compute the area under the graph of 1 over x when x is from 0 to 1. Probably still I'm going to mention that. The function is 1 over x in this particular case, right? So geometrically, we're trying to compute the area from 0 to 1, right? Under the curve, under the graph of 1 over x, when x is from 0 to 1. Okay. Two steps. The first thing you do is to now look at the graph. On the interval from 0 to 1, the function is only undefined at 0, right? The function is defined at any number from t to 1, where t is a number slightly to the right of 0. Now look at the mouse cursor. Does that make sense? So the first thing you do is to compute the definite integral from 0 to t, from t to 1. From t to 1, you compute the integral. Still mention t is a number, you imagine t as a number slightly to the right of 0, okay? But strictly speaking, you compute the definite integral when t is in between 0 and 1. Okay. Maybe for t in between 0 and 1. We compute the definite integral of that. It's possible so because the function is continuous on the interval from t to 1. T is a number slightly to the right of 0. Okay. We evaluate that. So this one should be simple, right? The definite integral from t to 1. Why do I write that again? All we need is to get a particular antiderivative of the integrand 1 over x. All of you guys know that. It's natural log of absolute value of x. So this time I do not have to include absolute value of x for the reason as I mentioned before. When computing that integral, t is a number to the right of 0. T is a number greater than 0. And x 1 over x. So x in the function are between t and 1, right? When x is in between t and 1, x is positive, so you do not need the absolute value notation. Okay. That's the antiderivative of the integrand, and then you evaluate the antiderivative from 1 to t. Okay. You plug in 1, I believe you have natural log of 1. So natural log of 1 is equal to 0. So the value of the function at upper limit is equal to 0. And then minus the value of the antiderivative natural log of x at the lower limit is equal to natural log of t. So minus natural log of t, right? Again, we do the things in two steps. The first step you do is to compute, to evaluate the function from t to 1, to evaluate the integral from t to 1. Okay, you imagine t as a number slightly greater than 0. So this one is essentially negative natural log of t. After the answer to step 1, the same as before, is a function of t. In the next step, it's actually the next step is kind of the new thing. Okay, in the next step, the integral now is improper, as a type 2 improper integral. Again, I'm looking for the definition. 0 is a point, a number. Is the reason why we have a type 2 improper integral, right? You need to give the definition of the type 2 improper integral. I'm looking for this step. Okay, you compute the limit as of the integral in type 1 from t to 1, and then dx in here, and then x, right? Actually, the key step is how to take the limit. Anybody want to tell me how we can take the limit? The limit is taken as t approaches what number? So please, the limit is taken as t approaches what number from what direction? From what direction? In most cases, the limit is a one-sided limit. Okay.
As it approaches 0?
Yeah, approaches 0 from the right, from the left. T is to the right of 0. Approaches 0 from the right. So basically, we were taking, as I mentioned earlier, t is a number slightly greater than t. T is a number slightly greater than 0. Okay, so t is to the right of 0. In most cases, we take one-sided limit. Okay, you imagine t as a number to the right of 0. And that's why we take the right-hand side limit. We take the limit as t approaches 0 from the right. So that makes sense? Approaches 0 from the right. Okay. And then we compute the limit as t approaches 0 from the right. You'll get the answer from step 1. You just take the limit as t approaches 0 from the right. You take the limit of negative natural log of t. Okay. Anybody want to tell me this limit? So what's the limit of negative natural log of t?
It's infinity.
It's infinity. It's actually positive infinity. Okay. I will show you why. Again, so geometrically, we're trying to compute the area under the graph of the function 1 over x. When x is from 0 to 1, 0 is not included. On the open, on 0 side is open interval. Okay. Now I will show you why the answer to the limit is positive infinity. Well, at this point, we need the graph of natural log of x. Okay, now you look at the graph of natural log of x. Okay, so maybe the graph of negative. We're trying to take the limit of natural log of x as x approaches 0 from the right, right? So how about we just look at this? I think the bottom line is, as long as you can remember the graph of the function natural log of x, you should be okay. Okay, now look at the graph. As x gets closer and closer to 0 from the right, as x approaches 0 from the right, natural log of x approaches negative infinity. You see it from the graph, right? In this question, we are trying to compute the limit of negative natural log of t as t approaches 0 from the right. The limit of natural log of t is negative infinity. So the limit of negative natural log of t is positive infinity. So does that make sense? So this one is infinity. Which means I think I can recover the other function. Which means the area under the graph of 1 over x, when x is from 0, not including 0, to 1, the area under the graph is infinity. It's not a finite number. Okay. So that's the geometric meaning. But in the question, we are trying to answer. I will show the question again. Okay. In the question, we are trying to determine if the integral is convergent or divergent. Okay. If it convert, so in this particular case, you see it's not a finite number. The answer to the integral, the answer to the improper integral is not a finite number. It's infinity. So we say the integral converges to infinity. Okay. So that integral, that's improper integral from 0 to 1. The integral of 1 over x diverges to infinity. Actually, in many cases, the most important thing you need to realize is you do need to realize this is an improper integral because the function is undefined at 0, right? So you cannot use FTC, you cannot use the fundamental theorem of calculus. Any questions about this? Do this thing in 2 steps, please. Okay. If you don't have any questions, then I'm going to summarize something called P integral for actually type 2 P integrals. Okay. It's kind of now let's recall I summarized the type 1 P integrals before, right? For type 1 P integrals, now you look at question 1. So that's a typical type 1 P integral in which the value of P is 2, right? This one is convergent. Now look at question 2. In question 2, you have a typical type 1 improper integral in which the value of P is 1/2. I think you can remember what I mean by P. Okay, so very shortly I'm going to write it down. This one is divergent. We mentioned that before, right? So basically, type 1 improper P integral is convergent when P is greater than 1, represented by question 1. When the value of P is less than or equal to 1, the type 1 improper integral is divergent. We have seen that last time I summarized. But for type 2 improper integral, it's kind of opposite. It's not totally opposite. It's kind of opposite. I think you can remember the answer, the integral in question 1, I mean type 2 P integral in question 1. So this one was convergent, right? This one was convergent. Question 2 was divergent. You look at your note, okay? And question 3, so we just did, is divergent. Okay. Now I'm going to summarize type 2 P integrals. Okay. Summary. Given a type 2, can I write that too? Type 2 improper P integral Actually, there are many cases for type 2 improper p integral. So even for type 1, so there could be more cases than what I summarized last time. I will try to include more cases. Okay. One case so could be in the form, so something like from a to b. On top you have dx. On denominator you have x minus a to the power of p. In this case, the integrand is undefined at a. So because the x value of a will make the denominator 0, right? I mean the denominator of the integrand. Okay. So this is one form of the type 2 improper integral. Okay. Actually, there's one other form I want to summarize together. One other form, so now let's also say from a to b. Okay. You have dx on top. I think we can make b the point with the problem. The function is undefined at b. All we need is to have the integrand, I think something like this, x minus b to the power of p. Again, these two integrals are called type 2 improper integral. I mean the integrals in an integral in one of the two forms is a type 2 improper p integral. Okay. I think I said it right. Again, there are two cases. Okay. The first case, is that, sorry, so something in my throat. The first case is that when p is less than 1, if p is a number greater than 0 and less than 1, probably we want to mention the case the value of p is greater than 1, than 0. Okay. Otherwise, it's not improper integral. You want to guess the conclusion when p is less than 1? Represented by question 1, I believe, right? In question 1, you had in part 2 question 1, you had a p integral in which the value of p is 1/2, so which is a number in between 0 and 1. You check your notes. Part 2 question 1, that integral is convergent. It is convergent. I told you it's kind of opposite to the case for type 1 improper integral, type 1 improper p integral. Okay, now the second case, if represented by question 2 and question 3, if the value of p is a number greater than 1, then it is, I do not have to write that, right? Then it is divergent. I mean greater than or equal to 1. Then the improper integral is divergent. For example, if on the final exam or any test or anything, I want you to determine if the following integral is convergent or divergent, you need to be able to answer the question using the conclusion for the p integrals. Okay. Now for example, if I want you to determine if the following integral is convergent or divergent, so now let's say from whatever number to whatever number. So now let's say from 1 to 2, the integral, now let's say 2 minus x to the power of 1.1. And probably I could include 2 more cases, so but I guess you have seen the meaning already. You have seen the pattern. Okay. So do you want to tell me, is this integral convergent or divergent? It's an improper integral for sure. So because the function is undefined at 2, right? It's a p integral. So because the value of p is 1.1, it's not exactly the same as the form in here, but it's still type 2 improper integral. Okay. The value of p is a number greater than 1, so it is divergent, right? So this one is divergent. I'm not sure it's very necessary or not, but I'm going to include two other forms. One other form is, so now let's say from a to b, you have dx on top. On denominator you have a minus x to the power of p. It's something like the question I just showed you, right? The last tab, if you want me to write all tabs, is kind of the following: from the a to b, dx on top, right? On denominator you could have b minus x to the power of p. Okay. Again, the last one is an improper integral. So because the integrand is undefined at b, right? B will make the denominator 0. Okay. I think if you can remember the 4 forms, it should be fine. Okay. You really do not have to remember. You just need to know the denominator is a linear function to some power p. Okay. And the function is undefined. The integrand is undefined at 1 of a and b. That's kind of that. Right? Any questions so far? Should be simple. Okay. For the assignment questions, I'm going to ask you to actually verify using a few particular questions to verify the p integral. Now, for instance, if I want you to evaluate the integral, you have to use the definition using 2 steps, right, to evaluate the integral to get the answer. Okay. All right. I guess what I meant is a question like question 4. Now let's work on question 4. Okay. Essentially, the question in question 4, the integral in question 4 is also a type 2 improper integral. We'll work on that next. Okay, we'll do that. The first thing you do is to identify at what point the integrand is undefined. The integrand now is undefined at 1. So 1 is the reason why we have a type 2 improper integral. Okay. So in the first step, you evaluate the definite integral from 0 to t. You replace the number, the point with problem with t. Okay. So later on, in next step, we take the limit as t approaches 1 from some direction. Okay. But you need to give some restriction on t. Okay. So this time t should be a number slightly less than 1. So do you know what I mean? T should be a number slightly less than 1. Okay, so that the integral from 0 to t is defined. It's possible to use the fundamental to compute the integral from 0 to t, right? More precisely, we want t to be in between 0 and 1. Okay, but you imagine t as a number very close to 1, slightly to the left of 1. We evaluate the integral of that from, so dx in here, right? And then on the denominator you have 1 minus x, the whole thing to the power of 1/2. You know the answer. You know the integral is going to be convergent according to the p integral. But for question 4, we're looking for a value. We want to determine the integral converges to what number, right? We do that first. Actually, I was a little bit confused for a little moment. Okay, we do not actually have a handy formula to evaluate the integral. So for this one, we have to use the substitution rule, right? We have to use substitution. We have to set u to be something. Okay, to evaluate the integral, we let u be you know how to choose u, right? We let u be anybody want to tell me how to choose u? Be 1 minus x, right? So that later on the new integral of u is going to be an integral of a power function of u. Okay. We let u be 1 minus x, and then we compute du, the same as before, right? Du is negative dx. The derivative of 1 minus x is negative 1. Okay. So dx is actually negative du. The integral we are trying to compute is actually a type 2, it's actually a definite integral from 1 to t, right? So we need to get the u values for x value of 0 and for x value of t. Okay, x value of 0 will give you u value of use the relation between u and x on top. Will give you u value of 1, I believe. Right. X value of 0, you look at the mouse cursor. X value of 0 will give you u value of 1. And x value of 1, x value of t will give you u value of 1 minus t. Now we are ready to convert the integral of x to a new integral of u. I'm going to keep on writing from here. Okay. Lower limit corresponds to lower limit u value of 1 to u value of 1 minus t. Okay. And then dx is negative du. You see that, right? And then on denominator you have 1 minus x is u, of course. You have u to the power of 1/2. Okay. I'm going to get a little bit more organized. So before we get antiderivative and so on, okay? It's not super necessary, but you see 1 minus t as a number less than 1. If that's if you do not feel comfortable about that, we can switch the lower and upper limit. Remove the negative sign, right? From 1 minus t to 1. Now you have the lower limit smaller than the upper limit. Okay. For the integrand, I'm going to write the integrand in terms of a power function of u. By that I mean u to the power of negative 1/2. Okay. It's better? Now we are almost ready to get the answer to step 1. Again, the answer to step 1 should be a function of t. So you have something like antiderivative of u to the power of -1/2 is u to the power of -1/2 and then plus 1. I'm using the power rule. Okay. -1/2 plus 1, you have +1/2. If you have exponent of 1/2, then the coefficient before that it should be 2. You invert 1 and 2, right? You invert the numerator and the denominator. Okay. That's the antiderivative. And then you evaluate the antiderivative from 1 minus t to 1. Right. We're almost ready. Okay. We're almost ready to get the answer for the first step. Now you imagine u to the power of 1/2 is actually square root of 2 square root of u, right? You plug 1 in, I believe you have 2. And then you plug in 1 minus t. You have 2 square root of 1 minus t, is that right? Can anybody double check I got this thing right? I think I got this thing right. Okay. So that's the answer to step 1. Okay. And then I mentioned before, the answer to step 1 should be a function of t, and then we take the limit of that function as t approaches something, and then we can have the answer. Okay. Now step 2. Again, the given integral is improper. It's because of that 1, the function, the integrand is undefined at 1. 1 is the reason why we have an improper integral. Okay. So in step 2, we are going to actually get the answer, the value of the improper integral. Okay. On numerator you have dx, you copy this one, and on denominator you have 1 minus x to the power of 1/2. I'm just copying the question. Okay. I'm looking for the definition. In step 1 we have from 0 to t, right? Dx on top. On denominator you have 1 minus x to the power of 1/2. Anybody want to tell me, so this time the limit is taken as t approaches what from what direction? The function is undefined at 1. We imagine t is a number slightly to the left of 1. So please, anybody want to tell me this time the limit is taken as t approaches what number from what direction? I know. I'm going to answer your question very shortly. Chad. So, but now answer my question, please. The limit is taken as t approaches what number from what direction? Approaches 1 from the left. Okay. Approaches 1 from the left. Yeah, that's right. So because when taking this limit, we mentioned before we take t, we imagine t as a number slightly to the left of 1, right? So that's why we take the limit as t approaches 1 from the left. The integrand is continuous on the interval from 0 to t when t is slightly to the left of 1. So that makes sense? Now I'm going to answer Chad's question. Okay. Why I want to switch the lower and upper limit? We learned a property before. Okay. In general, if okay, now let's use some particular numbers. Why I use AB. Now, for instance, for any function, if I want you to evaluate the integral, now let's say from 2 to 1, it's possible, okay, of any function, the integral of any function. If you don't feel comfortable to see the lower limit 2 is greater than 1, and then you can do something to fix it. There's a relation between the integral of any function from 2 to 1 and the integral of the same function from 1 to 2. The relation between these two integrals is the first integral is the opposite of the second integral. I did that in here so because 1 minus t is less than 1. I told you it's not super necessary to do that. You can use the fundamental theorem. So just from here to this step, eventually you'll have the same answer. Okay, cool. Yeah. Why we had negative is here. Sure, thank you. Cool. I think you got it. Again, I'm looking for the step in the box. This is actually the definition of type 2 improper integral. The definition of the improper integral. Okay. And then using the answer you got in from step 1, we take the limit as t approaches 1 from the left. Okay. The answer to step 1 is 2 minus 2 square root of 1 minus t, right? This limit is simple to compute. You just realize the function is elementary function, right? So defined at 1. So this time the function of t is defined at 1. You just plug 1 into the function, you have the answer, right? Square root of 1 minus 1 is equal to 0, right? So the final answer, I believe, is 2. So we say the integral converges to 2. Okay. So the given integral converges to 2. Right? Any questions? Any questions about this? If you don't have any questions, we'll move on to do more on this list. The next two questions, they should be simple actually. Okay. Now let's work on the questions one by one. Actually, the next question is kind of interesting. So probably you are going to see a question like that on the final exam. Okay, that's a simple question. Actually, you know antiderivative of 1 over square root of 1 minus x squared. So we work on this question together. Okay. For this question, it's not acceptable to use the fundamental, to use FTC. I'm trying to say it's wrong if you just do this, the integral from 0 to 1. If you just give me the answer like the following, it's wrong. You know the antiderivative of the integrand is inverse tan, right? Sorry, inverse sine of x. Okay, and then you plug in, you evaluate the antiderivative from 0 to 1. By that we mean you evaluate the antiderivative at 1 and at 0, and then you get the difference. Inverse sine of 1 minus inverse sine of 0. Inverse sine of 1 is half pi. Inverse sine of 0 is equal to 0. So your answer would be half pi. This way is wrong. This way is not acceptable. Anybody want to tell me why this way is wrong? This is actually an improper integral. The integrand is undefined at 1. 1 will make the denominator 0. So the function is not continuous on the interval from 0 to 1. I mean, the function is not continuous on the closed interval from 0 to 1. So this is not the right way to do the question. Because the integral is improper, so you have to use the way to do improper integral, right? I hope it's not too confusing, but I'm trying to say you have to do it properly for this improper integral. Yeah. I will show you how to do. Although the other way, you also get the right answer. Eventually, the answer is going to be the same, but still. Still, the integrand is undefined at 1, the same as the last question. Okay, the function is continuous at any number from 0 to t, as long as t is a number slightly to the left of 1, right? So we take t as a number from 0 to 1. You imagine t as a number slightly to the left of 1. Okay. We are going to evaluate the integral from 0 to t. Okay. Now we can use FTC, the fundamental. This time the integrand is continuous on the closed interval from 0 to t, right? So that's why we can use FTC, the fundamental theorem of calculus. Antiderivative of the integrand is inverse sine, right? Inverse sine of x. This one you do not need any substitution. Okay. From 0 to t, you evaluate the antiderivative from 0 to t. I think you have inverse sine of t, right? Minus inverse sine of 0. Inverse sine of 0 is equal to 0. I will give you one more step. So the final answer to the first step, the answer to the first step, so not the final answer. The answer to the first step is inverse sine of t. Right. And then in the second step, we do the question using the way dealing with improper type 2 improper integral. Okay. The given integral, again, it's super important to realize this is an improper integral. This is a type 2 improper integral. Okay. The definition for the type 2 improper integral is the following. We evaluate the integral from 0 to t. T is a number to the left of 1, right? And then you copy everything here. Again, t is a number to the left of 1. You imagine t as a number very close to 1. Okay. So the limit is taken as t approaches 1 from the left. So does that make sense? Actually, the limit part, I have always been confused. In most cases, the students are better than me at this. People can always tell me the right thing here. I guess you can follow me now. Okay. Again, in the box is the definition of type 2 improper integral. Okay. So you just take the limit as t approaches 1 from the left, and then the limit of inverse sine of t. Inverse sine of t is elementary function. To get the limit, all we need is to plug 1 into the function. So the final answer is the same, right? Inverse sine of 1, which is half pi. It's half pi, right? To get the inverse sine of 1, you think sine of what angle in radian is equal to 1? Sine of half pi is equal to 1, right? So that's why inverse sine of 1 equals half pi. A little review on how inverse trick is defined. Okay. I guess one of my intentions on this question is to show you in some cases you cannot use the FTC. You have to do it properly using the way to deal with improper integrals. Okay, now question 6. Now let's do question 6 together, okay? Antiderivative of natural log of x. Antiderivative of 1 over x is the absolute value of natural log of x, right? You get antiderivative of 1 over x, so which is natural log of absolute value of x. And then you evaluate the antiderivative from -1 to 2. Plug 2 in, you have natural log of 2. Plug -1 in, you have natural log of absolute value of -1, so which means you have natural log of 1. Natural log of 1 is equal to 0. You have final answer of natural log of 2. Is that right? I was trying to trick you. Is that right? Is this right? So this is wrong. This is wrong. So this is absolutely wrong. Why? Now look at the interval on which the integral is calculated. The integral is on the interval from -1 to 2, and the integrand is 1 over x, right? 1 over x is undefined at 0. 1 over x is undefined 0. 0 is in the interval from -1 to 2. So this is an improper integral. You cannot do it this way. Okay. I think last year on the final exam, I gave people a solution like this. I wanted people to tell me why. So this is wrong. I think I told people this is wrong. I was just asking you, why is this wrong? To answer why this is wrong, you just say the integrand 1 over x is undefined on the interval from -1 to 2. Or you say the integrand is discontinuous on the interval. So we cannot use the fundamental theorem of calculus. Now I will show you the proper way to do this question. Okay, now you look at I think we did a few questions, something like case 1, in which the function is undefined at a, the lower limit. We also have seen something like question 2, in which case the function is undefined in the first case the function is undefined at b. In the second case the function is undefined at a. We have seen some cases. Okay. Now we are on case 3. If the function is undefined at a number in between a and b, at a number c is in between a and b, okay, then we need to divide the integral into two integrals. So maybe dividing is not a good word. We need to convert the integral to two integrals, okay, which is the case in question number 6. The integrand 1 over x is undefined at 0, so it's a type 2 improper integral, right? So what we do is to convert the integral to the sum of two integrals from -1 to 0. I think the function is undefined at 0. You have no other choices. You have to use the midpoint of 0. It's not midpoint. You have to choose the point 0 in between -1 and 2. Okay. I mean, in any case, the given integral is equal to that. It's equal to the sum of the two integrals. Right. So what is the right answer? Each of these two integrals is actually a p integral, right? In which the value of p is equal to 1. So you can just use the answer to the p integral. Okay. Now, the type 2 improper p integral. So now let's say from 0 to 2. This is a particular case. This is a particular p integral with the value of p1, right? You see x to the power of 1. Now the p integral of that is divergent. You remember when the value of p is less than 1, the type 2 improper p integral is convergent, right? When the value of p is greater than or equal to 1, it's divergent. So this is divergent. If one of the two integrals is divergent, then the whole thing is divergent, of course, right? Therefore, the given integral is divergent. Okay. So any questions about that? Again, so this question is designed for case 3. After we learn improper integrals, so be careful when you're using FTC, the fundamental theorem of calculus. Okay. You need to check if the integrand is continuous on the interval or not. If you look at the graph of natural log of x, you see the function natural log of x is undefined at 0, right? Actually, the vertical axis is vertical asymptotes. Okay. Now we are trying to evaluate the integral from 0 to 1. Is that right? We're evaluating the integral from 0 to 1. You know the answer is either a negative finite number or negative infinity. We don't know yet. Okay. we're going to see, we're going to calculate. Natural log of x is undefined at 0. Okay, it's undefined at 0. So that's an improper integral. Okay. To evaluate the integral, we need to choose a t. Choose t slightly to the right of 0. The interval we are talking about now is from 0 to 1, right? You make t slightly to the right of 0. We are going to evaluate the integral from t to 1. Now you look at the graph of the function. As long as t is slightly to the right of 0, so not equal to 0, the function natural log of t is defined, is continuous on the interval from 0 to t. I mean from t to 1. Now let me try again. Okay, the function is continuous from t to 1, so it's possible to apply FTC, the fundamental, from t to 1. Does that make sense? So we evaluate the integral from t to 1, the integral of natural log of x. Okay. This is a typical form for using. So anybody want to tell me the integration technique you want to use to evaluate the integral from t to 1 natural log of x? Actually, when we learned integration techniques, I summarized many forms. So this is a typical form for using by parts formula, integration by parts. Okay. To use the by parts formula, you choose u dv and so on, right? So in this case, we choose u to be. You have no other choices. You have to choose u to be natural log of x. And then you choose dv to be dx, right? And then you compute du. To use the by parts formula, you need du, you need a v, right? So du is equal to 1 over x, the derivative of natural log of x, and then times dx. And then v is you need a particular antiderivative of 1. Okay. I think v is equal to x. Right. At this point, we can use the by parts formula for the definite integral. Okay. By parts formula for the definite integral. So here you have uv, u times v. In this particular case, you have u times v, you have x times natural log of x. So do not forget to evaluate that function from t to 1. Again, I'm talking about integration by parts for the definite integral. Okay, the general formula is something like this. From a to b, if you have the form of u dv, it's computed using uv minus v du. So do not forget the integral here is taken from a to b, and also you need to evaluate u times v from a to b. By this notation, we mean evaluate uv at b and minus the value of uv at a. So just review integration by parts for the definite integral if you forgot about the formula. Okay. Minus the integral of v du. v du in this particular case is from t to 1, right? From t to 1, v du. So v is x, du is so do you just have dx in here? If you want more steps, it's x times 1 over x. X and x is cancelled, right? So you just have the integral of 1. You have dx in here. Okay, now we're going to get the answer to step 1. That's step 1. You plug 1 in, okay? You plug 1 in. Okay, I'm going to run it a little bit slower. You plug 1 in, you have 1 times natural log of 1. The whole term is 0. Can you start for multiplication? I just do not want to be confused with x. And then you plug t in. You plug t into that function. I think you have t times natural log of t, so there's nothing you can do about that. So temporarily you leave this one like that. Okay. And then for the second part, antiderivative of 1 is equal to x. And then you evaluate the antiderivative from t to 1. Okay, the first term I believe is 0. Actually, I forgot what to do, so we'll see what's going on. Okay, it's not in my memory. In most cases, I can draw things from my memory, but I forgot what's going on in this case. Okay. Again, the first term is equal to 0. Natural log of 1 is equal to 0, right? I'll copy the second term, so it is t times natural log of t. And then for the last term, you plug 1 in, you have 1. And then you plug t in. Subtracting a negative number, you have a positive number. You just have positive t. Okay. Anybody want to double check I did not mess anything up? I think I'm okay. I'm probably okay. That's the answer to step 1. Okay. And then in step 2, we take the limit of that function. Take the limit of the function as t approaches 0 from the right. In the second step, I'm looking for the definition. Originally, we wanted to compute the improper integral of natural log of x from 0 to 1, right? X value of 0 is the reason we have an improper integral. You replace 0 with t from t to 1, right? And then we take the limit. So because t is to the right of 0, very close to 0, we take the limit as t approaches 0 from the right. So let me know if you see anything wrong. Okay. Natural log of x dx in here. Okay. The box part, we get the answer to the box part from step 1. So we just take the limit as t approaches 0 from the right. Okay. Negative t times natural log of t minus 1 and then plus t. We have the limit of a function with 3 terms. We evaluate the limit term by term. I have to move on to the next slide. I hope everything is moved over. Now look at the mouse cursor, okay? So later on we're going to figure out the limit of the first term, but the limit of the second term is -1. The limit of the last term is equal to 0. So we end up with something like the limit. Now let's say as t approaches 0 from the right. So here we have minus t times natural log of t. We're going to handle that limit later. Okay, we leave out negative sign. The limit of the constant of -1 is -1. The limit of t is equal to 0. So we plug 0 in here. So all we need is to evaluate negative as t approaches 0 from the right, t times natural log of t. Okay. This limit is a little bit weird to evaluate, but whenever you see a harder limit, do not forget about the L'Hopital's rule. Okay, I think you are going to see a question like that on the assignment. Sorry, I forgot to minus 1. Okay. We evaluate the limit of t times natural log of t separately, okay, as t approaches 0 from the right. Okay, we have to use the L'Hopital's rule. I think it's not too long ago for you guys to do L'Hopital's rule. I think you did that for the midterm, right? Convert a function to the form of a quotient so that you have an indeterminate quotient. I believe at least you can follow me. Okay. As t approaches 0 from the right, now the numerator approaches -infinity. The denominator approaches infinity. So it's an indeterminate quotient of type infinity to, -infinity to infinity. So it's permissible to use the L'Hopital's rule, right? To use the L'Hopital's rule, you write L here, okay? And then you differentiate the numerator, differentiate the denominator, respectively. Okay. Differentiate the numerator, you have 1 over t. The derivative of natural log of t is 1 over t, right? Differentiate the denominator, you have -1 over t squared. I told you to memorize the derivative of 1 over t before, right? So you end up with simplify a little bit, okay? You have the limit as t approaches 0 from the right. Do you have negative t? You have negative t, right? I will show you why. So in that circle, so basically you have 1 over t divided by -1 over t squared. So by that we mean you have 1 over t times invert and multiply, right? That's how to divide two fractions times -t squared. That's how you get a negative t, right? So this you have. So what's the answer to that limit? So this limit is equal to 0, right? You plug t value of 0 into the function, you have the limit of that term is equal to 0. So the original limit we are trying to compute is equal to -1. The statement of the comparison test is here. It's on this screen. Now look at the screen. On the screen you have the statement of the comparison test. I said the comparison test. You look at the mouse cursor. Okay. The statement is looking kind of weird. You just remember, okay. Now you look at that conclusion. Okay. You just look at the first two lines. So maybe you concentrate on the first item, on the dotted item, on the dot item, on the first item. Okay. You just remember. Actually it's true for both types, for either type 1 or type 2. This conclusion says if the integral of a bigger function is convergent, you see f of x is bigger than the g of x. Now concentrate, now listen to me. If the integral of a bigger function is convergent, then the integral of a smaller function is also convergent. That's the meaning. I want to repeat, if the integral of a bigger function is convergent, then the integral of a smaller function is also convergent. I will show you the meaning. I will show you the meaning graphically. I hope it's not too hard to understand. Okay. So now let's say that's point A. If we are trying to evaluate the type 1 improper integral from A to infinity. Now we are talking about the improper integral, the type 1 improper integral of a function from A to infinity. I think in the statement we are trying to make f of x bigger than g of x, right? Okay, from A to infinity, if the function f of x is something like this. So now let's recall that's the graph of y equals f of x. The integral is convergent. It means the area under the graph of the function from A to infinity, this area is a finite number. I mean, the integral from A to infinity, the integral of the function f of x is convergent. The area under the curve is finite. Okay, so geometrically it means that. If the integral of a bigger function is convergent, you imagine there's a function g of x, so which is smaller than the function f of x. Of course, g of x is in between 0 and f. Okay, g of x is always positive, and also g of x is less than f. So do you see the setup in here? The condition is that g of x is greater than or equal to 0 and less than f. So that's the case in here, right? G of x is less than f and above the horizontal axis, greater than or equal to 0. I hope it makes sense. If the area under f of x from A to infinity is a finite number, then the area under g of x from A to infinity is also a finite number. It means if the integral from A to infinity f of x is convergent, then the integral from A to infinity g of x is also convergent. So does that make sense? Yeah, that's the meaning. Actually, that is the statement. If you want to do math major, that's exactly the way to prove it. Mathematicians like to prove things, of course. Okay. Again, to remember that, you just remember if the integral of a bigger function is convergent, then the integral of a smaller function is also convergent. All the functions are positive. Okay, you cannot make the function negative. And likewise, I also hope it's not too hard to understand. You look at the second conclusion, okay? The second conclusion, it means if the integral of a smaller function is divergent, then the integral of a bigger function is also divergent. So that makes sense if the area under g of x is infinity, the area under f of x is also infinity. Again, both functions are positive, are non-negative. These two conclusions are called comparison test. It's used to determine some functions convergent or divergent, using some other functions convergent or divergent. Actually, the same conclusion is true for type 2 improper integrals. For type 2, the same thing, okay? If the integral of a bigger function is convergent, the integral of a smaller function is also convergent. Both functions are non-negative. And likewise, the integral of if the integral of a smaller function is divergent, then the integral of a bigger function is also divergent. The same story. I hope it's not too hard to understand, okay, using the graph I just drew from here. How can that comparison test, how can the statement useful for determining some integrals convergent or divergent? I'm going to use two particular questions to show you the meaning. I think I have enough time to talk about this. Okay, now look at the question on screen. In the question, you're not required to evaluate the integral. We just determine if the integral is convergent or divergent. Again, we just determine if the integral is convergent or divergent. Okay, it's not quite possible to evaluate the integral in this particular case, actually. If a question like that is on the final exam, it's probably a question designed for you to get more than 95%. I'm trying to say, I know not many of you guys are good at things like inequality stuff. I know it's a weaker point in high school, but I will try to let you understand this. Okay. The given integral is e to the power of negative 7x and then times absolute value of sine of x. So do you want to recall e to the power of anything is always positive? The graph of e to the power of x is above the horizontal axis, right? It's something like that. I'm trying to say the whole function is non-negative. The whole function is always greater than or equal to 0, right? It's not negative. The idea is we want to show this integral. Now I'm going to actually, for the assignment question or whatever question, I will ask you to prove that thing. I'm not going to ask you to guess the integral is convergent or divergent. I'm going to give you the conclusion. By that I mean I'm going to tell you the integral is convergent or divergent. I want you to prove that. Okay. In this case, I'm going to modify the question to something like the following. I want you to prove that integral, that type 1 improper integral, is convergent. Okay, to prove an integral is convergent, you need to find a bigger function that is also convergent. By that we mean you need to do something to find a slightly bigger function than that. Not too big, okay? By not too big, I mean you want the bigger function to be convergent. Anybody want to tell me want to guess a slightly bigger function, which is also convergent. Remember the property of sine of x. Sine of x is always in between 0 and 1, right? Remember the graph of sine is isolating in between 0 and 1. It's isolating in between -1 and 1. Sine of x is always in between -1 and 1. So absolute value of sine of x is always in between 0 and 1. So that makes sense? Again, we are trying to get a bigger function, so not too big. By not too big, I mean you want the bigger function to be convergent. Okay. The slightly bigger function I want to use is e to the power of -7x. So that makes sense? I want you to understand the inequality is true. Okay. Because the absolute value of sine of x is always in between 0 and 1, including 0 and 1, so that inequality is true. Okay. Now you need to show the integral of e to the power of -7x is convergent. Now I'm going to do that in one step, okay, to save some space and time. Again, we make the function a little bigger, so not too big. We want to make the function, we want to show the bigger function is convergent. We evaluate that the integral of the bigger function, okay, it's computed using now the definition, okay, from 0 to t, the limit as t approaches infinity. This is the only function I want to do things in one step. It's because I think we have seen too many questions like this. It's not too hard for you guys to follow now. Okay. That's the definition of the type 1 improper integral. Okay. And then you know antiderivative of the integrand. Antiderivative of the integrand is e to the power of -7x. And you need -1/7. I think you know that. We have seen something like this many times when we do integration by parts and so on, right? That's the antiderivative. You need to evaluate the antiderivative from 0 to t. Okay. And of course, so do not forget the limit. Alright. And then we take the limit as t approaches infinity. You plug in 0 and then you plug in t. I think e to the power of 0 is equal to 1. I think you are going to end up with, I will jump a little bit quicker, okay? You check the signs. I'm pretty sure I got this right. So the inside part, the answer to the integral, to the definite integral, is 1/7. You plug 0 in, you have e to the power of 0 is equal to 1. And then minus 1/7 e to the power of -7t. That's the answer to the step inside brackets. We take the limit of this, okay, as t approaches infinity, e to the power of -7t. Okay, I will try to say it this way. As t approaches infinity, -7t approaches negative infinity, and then e to the power of -7t approaches 0. -7t gets larger and larger negative. You look at the graph of e to the power of x. Okay. As a number gets larger and larger negative, e to the power of a larger and larger negative number gets closer and closer to 0. By that we mean the limit of the second term is equal to 0. So which means the answer to the definite to the improper integral is 1/7. I hope I'm not running too fast, but it's nothing but evaluate the definite integral. In the brackets you have what we call the step 1. The answer to step 1 is inside the brackets. You take the limit as t approaches infinity. Okay. So the answer to that integral is 1/7, which means this integral is convergent. I will write the full sentence. So the integral, the type 1 improper integral from 0 to infinity e to the power of negative 7x dx, that improper integral is convergent. Right. Now look at the first line. Now look at my mouse cursor. Okay. Both functions are non-negative. The bigger function is convergent, so the smaller function is also convergent. Okay. Now I can say something like, by the comparison test, the given integral from 0 to infinity e to the power of negative 7x, absolute value of sine of x, is also convergent. I'm going to summarize a little bit of what we did. Okay, to show an integral is convergent, you get a new function, slightly bigger, but not too big. You want this function to be convergent. If it's too big, then it would be divergent. Okay, you make the function a little bigger, and but not too big. Okay. I think in past many years, when I say this, people said that you have seen the same idea in chemistry, in biology, or those courses, probably. And then you need to show the bigger integral is convergent. Now the comparison test says if the bigger integral is convergent, then the smaller integral is also convergent. That's how we prove the smaller integral is convergent. I hope it's not too confusing, okay? One more question. We're at that. The question I want you to do is to show this integral is divergent. I remember this integral is divergent. I want you to show this integral is divergent. So try to follow me, okay? So this time it's an improper integral. You do need to realize it's an improper integral. The function is undefined at 1. The function is undefined at 0. Right? 0 will make the denominator 0. Okay. We want to show this function is divergent. Now the integrand is x times e to the power of x. The interval is from 0 to 1. Okay. It's kind of opposite to the other question. So this time we want to get a smaller function. We want the smaller function to be divergent. Remember, x value is in between 0 and 1. Okay. We want the inequality to be true when x is in between 0 and 1. Actually, x cannot take 0 when x is greater than 0 and less than or equal to 1. Okay. I know this thing is kind of weird. I'm going to tell you the smaller integral. Okay. So does that make sense if the whole thing is on the denominator? Okay. If you make the denominator bigger, then the whole thing will be smaller. Remember, x value is in between 0 and 1. I will tell you the function. Okay. Now try to understand. The denominator, the function I'm going to use is x times e to the power of 1. So basically x times e. On the numerator you have 1. Okay. This is true for any x in between 0 and 1. Probably you are not convinced. I will convince you right now. Okay, I will convince you right now. Okay, when x is in between 0 and 1, greater than 0 and less than or equal to 1. So does that make sense? E to the power of x is less than or equal to e to the power of 1. So basically x is always in between 0 and 1. I'm going to replace x with the largest number on the interval. Okay, this equation is true. This inequality is true when x is greater than 0 and less than or equal to 1. Okay. And then we invert the two functions. By that I mean we take the reciprocal of the two functions. Okay. E to the power of x in here. If we take the reciprocals, then we change the direction of the inequalities. So that makes sense. And then we multiply two sides of the equation by 1 over x. It's permissible because x is in between 0 and 1. In particular, x is always positive. So we have 1 over x times e to the power of x is greater than or equal to 1 over e times x. Right? This is true when x is in between 0 and 1. I hope you can follow me now. Okay. Anyway, the only thing I need is the first line. I showed you why. Okay. Now we want to show the integral of the smaller function is divergent, right? We take the integral from 0 to 1, the integral of the smaller function x times e. E is the constant. Okay. You write dx in here. Yeah, probably. Okay. E is a constant. Actually, it's the same thing as 1 over e times from 0 to 1. That integral. Okay. So does it make sense? This integral is divergent. It's a p integral. Without looking at the constant, is the p integral with the p value of 1. When the value of p is 1, this integral is divergent. Okay. Now the integral of a smaller function is divergent, right? On the interval from 0 to 1, of course. That's an improper integral. So the integral of the bigger function is also divergent. Again, by the comparison test, the integral of the bigger function is also divergent. Okay. I know the question could be a little bit hard for some of you guys because inequalities, you did not train too much about the inequalities in high school. That's probably the reason. Question 2 is going to be on the assignment. I'm going to give you some hint. After that, we are done. I think I still have a few minutes. This question is going to be on the assignment. The question on the assignment is going to be something like the following. Okay, I want you to prove this integral is convergent. I just show you one thing. Okay, it's kind of hint. To evaluate the integral, we need to consider x value is greater than or equal to 5. Actually, it's from 5 to infinity. You look at the integral. Okay, the integral is taken from 5 to infinity, so x value is greater than or equal to 5. Right? By that we mean when x is greater than or equal to 5, I want you to show this integral is convergent, x to the power of 1.1 and then plus 2. To show this integral is convergent, you need to get a bigger function. To show this integral is convergent, I'm sorry, I forgot dx. To show this integral is convergent, this is the integrand. You need to get a bigger function when x is greater than or equal to 5. You want the bigger function to be convergent. Anybody want to tell me on the right hand side which function is slightly bigger and also convergent? To make the whole thing bigger, you can make the denominator smaller. Anybody want to write in the chat or speak up, tell me which function you want to use as a bigger function? The bigger function is convergent. To make the function bigger, to make the whole thing bigger, you want to make the denominator smaller. When the denominator is smaller, the whole thing is bigger. Yeah, it's just 1.1 x to the power of 1.1 on denominator. Yeah, that's right. Yeah, that's good. I want you to realize this 1.1 that's circled is smaller than the circled on the left hand side. So the whole thing on the right hand side is bigger, right? I want to repeat, to make the function, to make the quotient bigger, you need to make the denominator smaller. If you make the denominator smaller, then the whole thing is bigger. So that makes sense? So you have a bigger function, and so that makes sense. The bigger function is convergent from 5 to infinity. The bigger function is the integral of the bigger function x to the power of 1.1. This integral is convergent according to the conclusion for the type 1 p integral, right? This is a particular case when the value of p is 1.1, so which is greater than 1. Okay, so this question is actually not that hard. Okay, you get a bigger function, so that the bigger function is convergent. So that makes sense. And of course, you need to say the whole thing, everything is greater than or equal to 0, right? When x is in between, when x is is greater than 5, both of these two functions, you look at the mouse cursor, the two functions are non-negative, right? So you see the bigger function, you say the bigger function is convergent. So the smaller function is also convergent. Okay, so that's probably enough hint for this question. Okay.